All right, so we saw in chapters 3 and 4 how we go about modeling the aerodynamic forces and moments. So chapter 3 was all about modeling longitudinal forces and moments in the aerodynamic sense, and chapter 4 was all about modeling the aerodynamic forces and moments in the lateral directional sense. So now we're going to take a very similar approach, but to model the thrust forces and moments. So we talked a little bit about these two diagrams. So these are figures 5.20 and 5.21 from page 289 of the textbook, and we saw how our thrust axis, which is the one parallel to the thrust vector of the engines, is described in terms of the stability and body axis systems. So we've seen this in the longitudinal plane and how we may have a toe up or toe down thrust vector angle with respect to the body axis system, and how we might have a toe in, toe out orientation of our engines in the lateral directional plane. So we're going to use these two descriptions to model the forces and how they affect the flight performance of our aircraft. So we're going to consider a general aircraft with N engines. So that could be 1, 2, 3, 4, 6, right? And they have an orientation both toe up or toe down, which is described by this angle theta t, and a possible toe in, toe out angle, which is described by this phi sub t angle. And they produce thrusts which could all be different. So they have generic descriptions T sub I, where our I corresponds to which engine we're describing, right? So then the components of thrust, F sub T, can be described in the X, Y, and Z direction, so that's with respect to the body axis system, remember, where we basically add up the thrust from all of the engines with the corresponding components based on the angles of toe up, toe down, and toe in, toe out, right? So this describes the force components with respect to the body axis system. So therefore, what we can do is we can convert that into thrust forces and moments with respect to the stability axis system. So that's the one with the subscript S's, right? And remember, this is the axis system which is rotated for angle of attack, right? So now we can write the force and moments based on that new stability axis system definition, right? So notice now that we have all of these components floating around which are all based on the angle of attack, but obviously not in the lateral directional sense, right? So only in the longitudinal sense. So those are the forces converted for the stability axis system, right, based on components of alpha 1, which is the steady state angle of attack. And then the moments are just given by the appropriate moment arm multiplied by the corresponding thrust, the corresponding forces, right, in each of those directions. So remember, the moment arms are given by little x, little y, and little z, right, as you can see floating around in these definitions, and they describe the distance between the center of thrust of the engine and the aircraft center of gravity. So for example, here in the y direction, center of thrust is here, and that's given the notation little y sub ti, which is the distance between the aircraft center of gravity and the center of thrust, right? So that's where this system has come from. I've tried to color coordinate this, right? So the blue ones, so in the X, Z, and in the pitch moment sense, right? Those are all the terms describing the longitudinal thrust forces and moments, and then the red ones describe the lateral directional thrust forces and moments. So that looks like a lot, it looks like a bit of a mess, but as always there are a number of fairly intuitive assumptions and assumptions that could be made for a general flight condition or a typical flight condition to reduce this system of equations down a little bit. So that's what I'm going to describe now. So some assumptions. So the first one is that the toe up and toe in angles are generally small, and typically if we have toe up and toe down, the toe up and toe down angle is generally larger than the toe in toe out angle, right? So again, using our small angle approximations, we can make this assumption and also this one. So again, the sine of a small angle is approximately a small angle in radians, and therefore when we multiply the sine of a small thing and the sine of our angle of attack in radians, that's approximately 0, so that's going to reduce down our system quite significantly. The other thing is that generally we operate with all of the engines at the same throttle settings and therefore producing the same thrust, and generally they have the opposite toe in, toe out angles, right? So if these ones are pointing in a certain degree, then these ones are also pointing in at the same angle, right? So the effects tend to cancel each other out due to that symmetry. And then what that leads to is no net side force components, right? So our FTY terms are all going to go to 0. And then also we're going to have no net moments in roll and yaw, because those side forces all cancel each other out from this diagram, right? So that significantly reduces down the complexity of our system. As you can see here, the side force is going to be approximately 0 if we have the symmetry of thrusts, and also we're going to have no roll or no yaw moments exerted due to those thrust components. So that's how the system is simplified down from the general form over here. So now what we're going to consider is small perturbations to each of these force components and moment components.